Hello, we are Group 38 and we would like to introduce our project Hermes, a real-time data acquisition module for a BESS BMS. Our group consists of 5 members: Erica for CPE, Gerson for EE, Crystal for CPE, Mariam for EE, and Omar for CPE. In our current environment, renewable energy is one of the main topics of industry advancement. On the forefront of innovation is the wind turbine. Based on its evolution, it has been positioned as a promising avenue for large-scale power generation. However, its efficiency and practical use have been questioned. With wind-propelled power generation, the system is at the mercy of the elements. On a perfect day, the resulting power output of a turbine farm is indisputably efficient. However, the introduction of natural fluctuations and weather conditions can introduce difficulties. The primary solution introduced was the Battery Energy Storage System, or a BESS. A BESS stores excess energy from the system and discharges it to the grid when needed. The energy is stored in units called cells, which are nested in an architecture of modules, racks, and blocks. In certain plant configurations, a BESS can contain over 180,000 cells. Naturally, with so many cells, there are going to be issues due to factors such as aging, unexpected loads, or simply the entropy of a system. A battery management system, or BMS, is used to monitor and stabilize cells. However, as the BMS becomes more specialized, the costs increase. For example, real-time data transmission, edge-based data collection, and cloud storage. And with that, we were introduced with a proposal: a cost-efficient and scalable edge-based module for a BMS that monitors a BESS and shifts it off to the cloud in real time. 3 project components would achieve the goal. 1. A data simulator to test the data that can be shipped from the BMS. 2. An edge-based data acquisition system, or EDAC, that analyzes the data at the source to achieve the most accurate real-time response. And 3. A cloud component that stores a subset of the data from the EDAC and a key performance indicator, or KPI report. Our response was Hermes. Hermes is a module designed to facilitate real-time data delivery from a BESS BMS. It implements a multi-computer grid configuration to process, analyze, compress, and transmit data to a dedicated cloud element. The project consists of 3 major components: the data simulator application, the edge-based data acquisition matrix, and the cloud element. Goals and objectives. Our goals include to develop a data simulator application as a stand-in for a BESS BMS, to create a scalable EDAC for the system, to configure a cloud element for data storage. Our objectives include, for the data simulator, generate realistic results, allow users to configure plant attributes. For the EDAC, establish 4-way communication, implement edge-based processing, and configure intelligent routing decisions. As for the cloud, store a subset of data along with the KPI report.
These are our engineering specifications. We chose 3 specifications to highlight, all of which are related to the EDAC. The first one is that the capacity of the data passed between nodes should be between 200 to 300 kilobytes, as the ESP32 can only handle 512 kilobytes, and we wanted to leave room for processing. The second specification is that the packet delivery success rate should be above 90% under normal conditions, and it should be above 80% if there is node failure that leads to rerouting.
The design. Hermes is modeled after a multi-computer architecture in which there is a data source and interconnected computers are assembled to pass along packets that are eventually aggregated in the central computer. Our main contribution to the design is the cloud, as well as a few modifications to the central computer that assist in integration. This is our data simulator. It is the starting point of our project and stands in for a BESS BMS. The user input is used to determine what influences the power development for the system. The top portion is the plant configuration, and it uses input values to convert into the power equation for a wind turbine. Once the values are satisfied, the best configuration allows the user to input different values for the different nested areas for a BESS. This determines the power distribution among the cells. Once the user decides a file name, a JSON is then created in order to hold the data that is stored locally. The COM ports are showed on the next page, and it allows the user to choose which COM ports are assigned to the entry nodes. Once the user clicks skip in the situation, the statistics are then shown.
So these are our entry nodes. We have 1, 2, 3, 4, and these are the exit nodes. We have 13, 14, 15, and 16. We have the intermediate nodes in the middle. We also have the EDAC divided into two halves. Each half communicates, the rows in each half communicate with each other using extenders. They could also communicate through UART in the entry nodes. For example, these two can talk to each other using the extenders. If, let's say, this node failed and it can't route up to it, it will route to the right here. And the same case in this half. The only nodes that can't communicate sideways are the exit nodes because they don't need to speak to each other. They will only receive data from the node behind them.
So for the cloud component of our system, a KPI report is generated using data from exit nodes of our EDAC. We currently see that the Arduino IDE has 4 terminals. Each exit node has to be compiled to subscribe to a specific topic, as well as defined with a device ID. Once the exit nodes are properly configured, the ESP32 attempts to connect to a Wi-Fi network. Then, they attempt to make a connection to AWS. And once that is successful, they subscribe to a specified topic. After these steps have occurred, they begin publishing messages received from earlier parts of the system to AWS. In IoT Core, we see that each topic that we have subscribed to has received a published message from the ESP32s. If we look through the messages of these topics, then we will see data that was sent from an earlier part of our system. As we navigate to SiteWise, we will then see that a subset of data will be stored in our assets. We have configured a data storage model for our modules and for our cells. Each of our assets contain a variety of measurements such as voltage, current, and temperature. These individual metrics from our assets are the key performance indicators that we will be sending to Grafana for later visualization.
This is our data simulator. As you can see, the user can input different fields and it throws different errors if they are incorrect or not filled in. And once you click send, the transmission begins between the ESP32 and the data simulator. What we're showing here is the sizing of the JSON. As you can see, at the configuration of 10 cells, it's going to be 1.46, and at the configuration of 200, it's going to be 26.94. And of course, these are important values as we are trying to stay under a certain threshold. And as you can see here, 134.87 for 1,000 cells. And this is for the demo that we do with Miriam and Crystal's part. As you can see, these are the sizes that we're getting, the 1.4, and it is pretty consistent and does not fluctuate too much.
This shows a row of the EDAC. I have my entry node here and my exit node here. The entry node will act as a stand-in for the simulator for the subsystem functionality demo. Entry node will now produce 4 JSONs. See they have different device IDs for the row. So this row has device IDs 1, 5, 9, and 13. Node 13 is the exit node, which will receive all the UARTs. Here it receives this one with the same device ID as it, and it processes it, and then it receives all the previous ones as well. Now I will demo the rerouting capability of the EDAC. Here we see that node 9 is not connected, so node 5 needs to reroute to node 6 and then send the information to this node. We see here where it was originally sending some data, and it started sending after I reset it. It was previously also sending some data beforehand. We have it sending data meant for itself, so it will process it and then send it. Here we see that it processed it and then it sent all the other data to node 5. So here we see it received 1, 5, 9, and 13. Once it receives 13, because node 13 is the one that is across from it, it will process its data, because node 13 did not get to process its own data because it never received it. So it'll process it here.
Here is our voltage regulator, which is connected to a power supply and electrical load. The power supply is outputting 12 volts and the electrical load is drawing 2.5 amps. And as you see, I lower the amperage and our voltage is outputting 3.3 consistently on the multimeter. To demo our switching regulator, we will use a mounted temperature sensor on our custom PCB. Here we can see the regulator powering 4 nodes. The code is showing room temperature is being outputted. I will now use my thumb to cover the temperature sensor, and we can see that the value gets a little warmer. And now I'll remove my thumb, and we can see the temperature is starting to cool off. This slide demonstrates the functionality of our UART communication between our custom PCBs. COM9 acts as the sender, and COM10 acts as the receiver. They are connected through general pins 16 and 17. We can see that the message was received. Our 2 custom PCBs are connected through TXA and RXA, which is a UART channel within the mounted I2C extender. COM9 acts as the sender, and COM10 acts as the receiver, and we can see we are receiving temperature and voltage values. A 219 sensor is outputting realistic voltage and current values. Here we see our mounted BMP 180 outputting realistic temperature values. Here 27 Celsius is about room temperature.
This is the fourth and final row of compression and decompression at 75%. I'll be collecting the data through the same manner as 0%, 25%, and 50%. After the data logger collects the data, I will then run the plotting code, similarly to the prior runs. The compression size versus accuracy chart shows the mean relative error when compressing the data to about 75% of the cells. The deviations in the data for current, temperature, and voltage shown at this level of compression demonstrate that there is an averaging effect happening with the values. As more cells get dropped, the less accurate the data is because the decompression having to bring back these missing cells due to interpolation is trying to pick up the slack. This is the speed gain versus accuracy chart. The compressed data clocked in about 5.3 seconds faster than the original data. This level of compression is about 0.1 seconds faster than the 50% compression. This level of compression has lost us about 25% accuracy in temperature and 4.8% accuracy in current.
Wi-Fi connect and the lights return. So we see bulk 4, we see bulk 3, we see bulk 2, we see bulk 1. And I customize it just so we can see changes in the values. So temperature for the cell, currently 31.4, and in Grafana, you should see that the temperature fluctuates. Okay, it's fluctuating between 10, 1, 10, 20, and 30, just as we expected. So because we send values of the temperature is currently for cell 1, is temperature is 1 for bulk 1. The temperature is cell 1 is going to be 10, 11, and then for bulk 2, and then for bulk 3, the temperature is going to be 21, and then bulk 4, the temperature is going to be cell 1, 31. For cell 4, we can verify that it's going to have the same behavior because multiple data is being sent and none of it is being overwritten because of the timestamp and processing done by our Lambda function.
This is our first run. We have our laptops hooked up to the system so we can monitor the data as it flows through it. Erica will now send the information from the simulator to the EDAC. You see here through my monitor where the data is flowing through the system. You see the first node receiving the JSON that belongs to device ID 1 and sending it to the next node. You see all these other nodes as well receiving the data that belongs to their row.
So data is still coming into the cloud. We can see in IoT Core that we receive 4 packets of data within the first topic, and each topic should receive an equivalent 4 packets of data. If we go over to the dashboard, we should see the modules updated that were sent within the last 5 minutes. We currently see data for 15 modules.
This is our second run. We also have our laptops hooked up to the system to see the data flow through the system, and Eric is now going to send information to the simulator. We see here in the EDAC the information propagating through the system. We see device ID 3, which is from a different row than device ID 1. We see it sending to the nodes in front of it. We also see it processing the JSON that has the same device ID as it, so this would be node 9.
For the cloud component, data from the exit node of the EDAC can be seen in AWS IoT Core. We can see that 4 packets were received from this specific topic. Each topic is set up to receive those 4 packets based on the 16 modules that we have created. And in Grafana, where we publish a KPI report, we can see that 15 modules have sent data within the last 5 minutes, and this satisfies our specification of 90% data retention.
This is run 1 for rerouting. So we have this node turned off and this node turned off, which means that when this node wants to send forward, it will not be able to, and it will have to reroute here. Same with the other node. I have my serial monitor connected to all 4 of those nodes to monitor this one as it reroutes and this one as it receives it and sends it over on the row. And now Erica will send the data from the simulator. Connected to serial 1. We have this node that's not connected. It's not able to send to serial 1, as you can see here. It tries to send to channel A. It's successful at sending to channel A, so that's received by the other node. So this is the rerouting, where it doesn't send to the serial 1 and it sends it to channel A. Here you see this one, it's returning from the extender, which means it's returning from a different row. When it returns from a node in its row, it'll return from UART. Here it's returning from channel A. So the rerouting was successful.
After data has been rerouted through the EDAC, at the exit node, data was successfully received in IoT Core. In one bulk, we received 8 packets, and
These are the 8 packets. In another bulk or topic, we received 5 packets successfully. And when we look at Grafana, if we refresh, we see that 9 modules sent data successfully. The result of 9 packets being sent was because malformed data was dropped and data that was formatted correctly was sent successfully. And this led to a success rate of around 80%.
This is run 2 for rerouting. In this run, this node is removed, so when this node tries to send to it, it will not be able to, and it will reroute to this one. Same for this node, it will not be able to send forward, so it will try to send to this one. Erica will now send the JSON from the simulator. See here that the JSON is being received by one of the nodes. We see in this one that it attempts to send, right, and it's not able to, so it sends to channel A. And we see here that it is returning from channel A, but previously it's returning from UART, so it means it's receiving both from the node behind it and from the node in the other row.
So data was received from the exit node of the EDAC after rerouting. In the cloud, in IoT Core, I got 8 packets published to one bulk, one topic. Got 8 packets. And for the second topic that was connected, I got 5 as well. And then in the dashboard, I got 9 modules published, and this was because of data. In the dashboard, I got 9 modules, and this was because of malformed data. The data that maintained its integrity was sent, and this is what we see in the dashboard.
This is run 3 for normal conditions without any node failure. We are using a PCB in place of 2 of the nodes. And Erica will now send the information through the simulator. You can see here in the code, in the serial monitor for the PCB, that it's receiving device ID 3. You can also see that it's sending to serial 1, which is the node in front of it. It's now also receiving the rest of the JSONs, so 7, and then it will be 11 and 15. And it's sending all of them to the node in front of it. You can also see how it processed device ID 7 because it has ID 7.
In AWS IoT Core, you can see that if we subscribe to one topic, 4 of the data packets are sent and received. And if we check with another one, we can see that it also sends 4 data points. If we go to Grafana and reload the dashboard, we can see that the data that hasn't had any issues, misconfigurations, or affected JSON packets, they're seen in the dashboard.
This is our 3rd run of the rerouting with PCBs. We have this node removed, so when this node tries to route forward, it will not be able to, and it will have to reroute to the PCB. my PCB is connected to the monitor here, so we see how it's receiving data. And Erica will now send the data from the simulator. You can see here on my screen that the PCB is receiving device ID 3 from the JSON, which belongs in its row. It is also receiving device ID 4. That one belongs to the row next to it, so that means that the rerouting has been successful. You can also notice that there's a difference between returning from UART and returning. When it returns from UART, that indicates that the communication is happening over serial in the same row, but when it returns normally, it's sending over the channel, which facilitates inter-row communication. We also see the rest of the JSONs arriving. We see 7, which belongs to its row, 8, which is from the row next to it, 11, 15, and all of it is being sent to serial 1, to the node in front of it.
Normally we don't send data from the data simulator twice, but in this case, we sent the data twice to ensure that not too many packets of data were lost during rerouting. We can see in AWS IoT Core that in topic 1, more than 8 packets of data were sent. And if we take a look at topic 2, we can see the same results. So in total, more than 16 packets of data were received in IoT Core. And if we take a look at our Grafana dashboard, Grafana filters out data that was malformed or duplicate, and it only shows valid data, and this is what can be seen in our dashboard.
This table shows our success rate after 10 runs under normal conditions. It averaged around 90%. This table shows our success rate after 10 runs for conditions in which there was rerouting. It averaged around 80%. This table shows the size of the JSON in relation to the number of cells in the module. As you can see, it takes quite a few cells in order to reach the maximum capacity for the ESP32.